Greetings to all. My name is Kiwan, and I am a second-year undergraduate student reading mechanical engineering at Heriot-Watt University, Malaysia. The title of my speech today is Keep Moving Forward, Lessons Learned from an Engineering Design Project. As a child, one of the most iconic films I remember watching was Meet the Robinsons. Do you remember it? It was a computer-animated comedy film produced by Disney in 2007, which I am sure is near and dear to every aspiring young engineer's heart back then. At least it is to me. The film revolves around a 12-year-old orphan named Lewis, who was an aspiring young inventor. However, his frequent failures led him to doubt his abilities as an inventor. One day, he meets another kid named Wilbur Robinson, who then took him to the future, where talking frogs and bespectacled dogs are a common sight, and eventually he met Wilbur's family, the Robinsons. You may ask, why is this one of the most iconic films of my childhood? Well, it is due to one particular scene. By this point, Lewis was invited by the Robinsons to have dinner with them. After the first course of spaghetti and meatballs, and a ludicrous food war, the next course was peanut butter and jelly, shot from a nifty gun onto slices of toast from a distance. However, the gun got jammed, and Wilbur persuades the initially reluctant Lewis to attempt to repair it. Unfortunately, the gadget malfunctions and creates a colossal mess, covering everyone and everything. Lewis apologizes profusely as he expects the Robinsons to get angry, but then...
You failed!
And it was awesome!
Exceptional!
Outstanding!
I did better!
From failing, you learn. From success, not so much.
If I gave up every time I failed, I never would have made the meatball cannon.
I never would have made my fireproof pants. Still working out the kinks.
Like my husband always says.
Wasn't that surprising? Who knew they would react so supportively to failures? Keep moving forward. Those three words have stuck to me like peanut butter stuck to the roof of your mouth after eating a PB&J sandwich. They ring even truer for me, especially in this past academic year, which I have completed fully online due to the ongoing pandemic. Why, you may ask? Well, let me share with you 3 lessons that I learnt from ensuring that I kept moving forward in one engineering design project in particular, in a little course I took last semester called Energy Studies. Anyways, in this particular engineering project, we were to form groups of 5. In those groups, we were to design and plan an electricity grid for an isolated island far from the mainland, which was looking at switching to 100% renewable energy. The energy sources available on the island were from the sun, the wind, and the rivers. There were 12 families, 18 couples, and 5 small businesses on this island. However, there was a catch. The island had no connection to the mainland. No electricity can be either imported from or exported to any other grid. All electricity needed must be generated on the island, and any electricity generated must be consumed on the island. It seemed we had our work cut out for us then. The first lesson that I learned from this project is that not all that glitters is gold. As I mentioned earlier, we had 3 potential energy sources to generate electricity on the island: the sun, the wind, and the rivers. We were given the option of either relying fully on one energy source, or a combination of two, or even all three. From the get-go, we were gung-ho about having all three to maximize the electricity we can generate. We were especially keen on relying on the hydropower generated from the rivers as a continuous base supply year-round to which solar and wind power can supplement intermittently. However, after further inquiry, it seems that hydropower was unsuitable for our purposes. This is due to the island being mostly flat, hence ruling out the possibility of building a dam, and the flow rates on the island being very small. Thus, the electricity that could have been generated from the run-of-river hydroelectric schemes is insignificant compared to that generated from onshore vertical axis wind turbines and solar photovoltaic panels. Hence, we learned that not all that glitters is gold, and in order to ensure we had a continuous electricity supply, we simply had to keep moving forward. The second lesson that I learned was that where there is a will, there is a way. This was due to one major problem that we ran into. To determine how our grid will supply electricity to meet demand, we created a model using the data given to us. This model also helped us determine the energy storage required for times when energy demand outstrips supply. We had hourly data of electricity demand from the consumers for one average year, as well as the hourly wind speeds. However, for the solar data, we were only given the GPS coordinates of the location of the island. From that, we generated the solar power data from a simulation package called PVSys, but it was only available in monthly values. This difference in resolution in the data had put a spanner in the works. Initially, we had decided to create a data model based on the daily data, converting the demand and wind data sets and simply dividing the monthly values from the solar data by the number of days in each month. However, this became a problem when it came to determining the energy storage required and its usage. This was so, as even if we consider the day as a whole as having greater electricity supply than demand, there might be particular times within the same day when demand far exceeds supply. This detail gets glossed over when using daily values. This was a salient consideration for these following two reasons. Firstly, some energy is lost when stored, depending on the efficiency of the type of energy storage used. Considering our final choice of regenerative hydrogen vanadium fuel cells, or RHVF, as our long-duration energy storage, this means that from the amount of electricity generated earlier in the day before storage, only up to 70% of this could be supplied by energy storage, due to this energy loss. Hence, instantaneous electricity supply and supply from storage cannot be treated the same way. Secondly, we were also seriously considering liquefied air energy storage, or LAES, which can only supply electricity for a particular period of time, after which the energy storage needs to be recharged. Therefore, we were trying to ensure that the maximum duration that the energy storage powers demand is less than the maximum duration that LAES supplied. Thus, how were we to estimate the hourly values for power generated from our solar panels? We already had our daily values in each month, so using the given GPS coordinates, we then started finding the daylight hours during which the solar panels produced power. However, we quickly realized that this could vary from month to month and did some research for our particular reference location. As the yearly variation in daylight hours was only around 2 to 3 hours, we decided that we varied the hours by season. Another thing that we realized as well was that it was unreasonable to assume that an equal amount of power was produced each hour during the daylight period. Again, we did further research and found that the amount of solar power generated was a function of the sine of the angle of the sun's elevation. We did find that we needed to adjust our values by a particular constant, the variation of which, through all the months in the year, was not dissimilar to a cosine function. The thing was, all of my group mates, bar me, thought that this endeavor was too time-consuming and not worth the effort, instead wanting to opt to explain the possible inaccuracies in the solar data in words, to quote one of them. However, I stuck to my guns and believed that, with some elbow grease, it could be completed. Several hours of tedious data manipulation later, and we got the hourly solar power data. We were as electrified as Benjamin Franklin's kite flying between the storm clouds. It was no small feat, but it does go to show that where there is a will, there is a way. And in this case, we were rewarded with a greater resolution in our model. Well, with that, we kept moving forward. The third lesson that I learnt was not to crack a nut with a sledgehammer, courtesy of another problem that soon hit us. From analyzing the data, it seemed that the amount of electricity we were producing in 1 year is far greater than what the demand can consume. And if it were all to be stored, then the energy storage would be rendered economically unviable. It soon dawned on us that we needed to find ways to reduce the supply and determine when to take our wind turbines and solar photovoltaic panels offline. Thankfully, the time taken for these to come online and offline were mere seconds, the deficit of which would be supplied by flywheels, our choice of short-term energy storage. At first, we decided to simply take some wind turbines and solar photovoltaic panels offline for long periods of time, but then it soon became untenable due to the near erratic nature of the change between periods of energy surplus and deficit. Even the manual adjustments in the model soon became extremely tedious to do. With that, I suggested that we might automate the process of taking the wind turbines and solar panels online and offline, and devise an algorithm for it to cut out the need for a human comptroller to manually manipulate outputs of the wind turbines and solar panels. As the overwhelming majority of our electricity was generated from the solar panels, we only imposed this algorithm on the solar panels to avoid extra maintenance which could arise from taking wind turbines in and out of operation, as the blades cannot be abruptly stopped, but rather spin slowly until they stop. The resulting algorithm had 5 variables, depending on whether the amount of stored energy is below the lower or upper thresholds, whether the generated electricity is greater than demand, whether the electricity generated from wind exceeds demand, and whether in times when electricity from wind is below demand, if there is enough electricity from the solar panels. Depending on these 5 variables, a proportion of the solar panels would then be taken offline, the exact proportion of which would be computed. That sounds very nifty, does it not? However, when we tested it on the model, we found that most of the considerations that I have mentioned had little impact on the effects we desired. Soon, that algorithm that we first had was reduced to only one variable, whether the amount of stored energy was above or below a certain threshold. This goes to show that sometimes we overcomplicate things when really there is a simpler solution waiting to be discovered. In essence, not to crack a nut with a sledgehammer. Just keep moving forward. Although we had recourse to a diesel generator in times of small supply deficits, we were glad that we could design an electricity grid that only required it strictly during emergencies, and one with a reasonable levelised cost of energy of 28 pence per kilowatt hour, as compared to that of the real-life exemplar on the Isle of Egg in Scotland at 20 pence per kilowatt hour. We were just 8 pence more per kilowatt hour than a real-life system, which is not bad at all, don't you think? In conclusion, this engineering design project has taught me 3 lessons. That not all that glitters is gold, that where there is a will, there is a way, and to not crack a nut with a sledgehammer. However, there is one chief thread that ties these 3 lessons together. If at first you don't succeed, try again. This has been the key in moving forward, in my experience at least, and this experience has been vindicated by others as well. It is well known that Thomas Edison, scientist and engineer, failed 10,000 times in refining the light bulb. When asked by a reporter, how did it feel to fail 10,000 times? Edison scoffed and curtly replied, I didn't fail 10,000 times. The light bulb was an invention with 10,000 steps. Whether this story is true or apocryphal is immaterial. The lesson remains the same, that by moving forward, even if it is a misstep, you are still one step closer to succeeding than when you do not move at all. Thank you, and remember,